Hello everyone, my name is Qinghao. I'm really excited to be here to present our work, Primo, Particle Learning-Augmented System with Interpretable model. This is a joint work with Harsha from Microsoft, Peng from SenseTime, and my supervisor, Tianwei and Yonggang from Nanyang Technological University. Firstly, I will introduce the background of machine learning application in system domain. With the emergence of machine learning research, there are more and more developers start to employ machine learning techniques to optimize their system. For example, there are many extraordinary systems across storage, cluster scheduling, networking, and security fields. In this system, ML brings awesome system improvements. However, although some systems are implemented as a prototype and demonstrate their performance in some research testbed, it's non-trivial to shift them to production environment. There are more concerns and challenges in practice. We summarize 5 common barriers that block system deployment. The first is the high training and tuning cost. Learning-augmented system requires frequent model fine-tuning or retraining to maintain the model performance. This is because system environment is dynamic change by scaling up or scaling down over time. And the workload may also change and cause the distribution drift. According to Microsoft operation experience, the cost often exceeds enterprise expectation, and performance is in the testbed might not match the performance in the production environment. In addition to the training process, the inference overhead is another significant concern. The common AI application lacks the face recognition and translation requires about millisecond scale inference latency. However, in some system scenarios, such as storage and networking, requires strict microsecond scale. Further, in some scenarios, due to the high concurrency, their computation resources is very restricted, including the CPU, memory, and the storage. Due to the strict inference overhead requirement, some of them meet the scalability issue. They work well in testbed scale, but they fail to handle the production scale environment. Further, they may cause some side effects to the main production workloads because ML models occupy too much resources. The third problem is insufficient data. As we know, ML is data-driven, and the data volume determines the model performance. And the model is more complex, more data is needed. Most systems can collect data from their history operation logs. However, in some scenarios, meet the data issue because the high data collection cost or privacy-related data issues. This blocks operators to obtain a qualified model. A possible solution includes data augmentation and scissors. However, this may include some bias and distribution drift and cause the inferior performance than the heuristic algorithms. To strive for excellent system performance, most learning-augmented systems rely on black box model, like the deep neural networks. This model takes some system features as the input data and obtain the system decision. It seems very simple and convenient. However, the whole decision process is opaque. It's hard to know how the model makes decision, and should I trust the prediction? This is because interpretability is important but often ignored. Operators need sufficient confidence to deploy them. However, current models cannot provide such confidence. Another interpretability-related issue is hard to make the adjustment. In practice, the system environment varies a lot. They may have different scale, different hardware configuration. One model may perform poorly in another environment, so accordingly, adjustment is necessary. However, most models are too complex for system operators to understand. For a naive MLP model, it's hard to determine the proper layers and the neuron configurations, even for an ML expert. So how to adjust the model? Is the adjustment correct? Always confuse operators. And the improper modification may cause severe performance degradation. Operators need guided or automatic model adjustment. In summary, there are 5 main challenges in deploying models, including cost, overhead, data, opacity, and adjustment. So, how to address these issues? There are some existing solutions focused on interpreting black box models, makes the system more transparent. For example, LinnOS and DeepEd focus on interpreting security applications, and the Metis apply for the networking systems. This works create another surrogate model to explain the original model. And the surrogate model is typically the simple interpretable models. However, this approach has significant limitations. They can provide individual explanation for individual predictions. However, they fail to explain the entire model. More importantly, they cannot provide fidelity guarantee for their interpretation. Their interpretation is unreliable and may be misleading. Moreover, they only consider the interpretation. They fail to handle other challenges, including the training cost, inference overhead, and the insufficient data issues. So, is there any solutions can solve all the challenges? Our answer is yes. Our idea is quite simple. Instead of interpreting black box model, why not directly adopt and optimize interpretable model? Common interpretable models are very simple, like the linear regression, logistical regression, and decision tree. By replacing the original model, we can obtain incredible benefits. First, these models are inherently intelligible. They can provide, we can get rich information from the model, and their interpretation are reliable. Besides, these models are simple and lightweight. They can significantly reduce the training cost, inference overhead, and data requirement. We understand the major concern of interpreted model is their model performance. So is there any trade-off between the model interpretability and the model accuracy? From our observation, interpreted model will not sacrifice model accuracy. For the input feature aspect, common AI application typically adopts the image pixel and word embedding as the input. They are very high dimensional and complex. On the contrary, ML-based system adopts some system states like the network speed and the workload features like the memory consumption as the input feature. They are meaningful and lower dimension. From the model scale aspect, common AI applications contains over 10 layers with millions to billions parameters. However, as summarized by last year's SIGCOMM paper, the common R-based system contains less than 10,000 neurons. They have much smaller scale and latency sensitive. Interpretable models have comparable performance and less overhead, hence they are more suitable for system scenario. Based on our observation, we designed Primo, prior-based interpretable model optimization, to assist the developers to design and optimize learning-augmented systems with interpretable models. Our objective is to achieve transparent, accurate, and lightweight learning-augmented systems. We find there are various systems. Based on their system requirement and the application scenario, we divide them into two categories. For the online systems, they need to make the promote response to real-time data. In addition to the model performance, they also need to consider the latency and the computation resources. As for the offline system, they have no latency requirement. They only need to focus on improving their performance. To this end, Primo supports various interpretable models. Besides, Primo optimizes both the model training and the post-processing stage of designing learning-augmented system. In the training stage, currently, Primo supports two types of interpretable models. The first is PrAM, a dictative-based method, as depicted by the diagram. It's actually the summation of a series of simple univariate or bivariate shape functions, so we can clearly understand each feature's contribution to the final prediction. This model is mainly designed to achieve better prediction accuracy. The second model is PrDT, decision tree-based methods. As shown in the figure, each decision can be clearly visualized. Due to its extremely simple structure, it is more suitable for online systems with strict latency and computation resource constraints. We also use the bias optimization to automatically search for optimal model configuration. It can quickly find the accurate and simple model. To support more general systems, we designed Distill Engine to mimic the behavior of the original model. It can well support IL-based system. Beyond the training process, we also support post-processing optimization. Note this is an optional step because the trained model typically already obtained satisfactory performance. We designed two post-processing tools. The first is monotonic constraints. It can add monotonic constraints to the shape functions in the PrDT model, PrAM model based on prior knowledge. This can achieve automatic model adjustment and fix the noisy data issues. We also provide a counterfactual explanation for guided model adjustment. It's aimed to find the smaller feature value change. In the evaluations part, we perform 3 case studies to illustrate how Primo can optimize SOTA learning-augmented system. The first system is LinnOS. It's aimed to accelerate flash storage I/O based on DNN prediction. It's an online system with strict latency and resource constraints. The second is Clara, an offline tool to generate SmartNIC offloading insights. It adopts various ML models. The third one is Pencil. It's an IL-based online video streaming systems. Due to the time limit, we mainly talk about the first case. The idea of LinnOS is quite intuitive. It collects the queue length and the latency of recent I/O operations and form 31 input features. These features processed by a 3-layer MLP model containing over 8,000 parameters. Then the model classify classify the current I/O operation into fast or slow. Our Primo implementation is quite similar with the bias optimization. We find that with only 3 input features without any pre-processing are sufficient for this task. And we obtain the learned decision tree model. From the tree model, this tree model is very simple. With only 4 layers, only 7 leaves. From the tree model, we can clearly understand how the model makes prediction for each makes decision for each prediction. We perform the performance analysis. From the finger is the CDF curves of Primo, LinnOS, and original Linux. We find Primo outperform other baselines. And for the average I/O latency, Primo achieved 2.5 better compared to the LinnOS. And the tail performance is also critical for the system. The bottom finger shows the tail percentile of the tail percentile the latency. We find that Primo can achieve up to 7.9 times reduction compared to LinnOS. We performed the effective analysis to understand where the benefits come from. For the inference overhead, the LinnOS needs to do the data processing and the DNA inference for each I/O. And we find that in some cases, the LinnOS may induce even a higher latency than the SSD access. However, for Primo, it needs to perform only up to 4 times if-else condition test. Is extremely lightweight. And from the finger, we can clearly see the Primo inference overhead is ignorable. Besides, floating point are not well supported in Linux kernel. The model weights of LinnOS and the threshold value of Primo need to be converted into integers through quantization. We find Primo have no degradation and achieve better accuracy. We also analyze the robustness. We find Primo are more stable to the perturbed inputs. There are more evaluations in our paper, such as adding monotonic constraints to Clara and use Distill engines to Pencil, all systems which achieve better performance. For more details and results, please refer to our paper. As a summary, first, it's non-trivial to deploy Learning-Augmented system in practice. We may meet serious challenges. To address these issues, simple interpretable models are excellent choices. We demonstrate they can outperform 3 SOTA Learning-Augmented systems, including LinnOS, Clara, and Pencil. And the operator needs automatic and guided model optimization to achieve better system performance. Our code is open source. Please check our GitHub website. Thanks for your listening. We welcome for any questions.